welcome also from my side to the second edition of this UK Biobank seminars by the N8. Yeah, my name is Jochen Einbeck. I'm from Durham, and it's my particular pleasure to welcome today Alex Casson from the University of Manchester as our speaker. Alex has a PhD in electrical and electronic engineering from Imperial College London. He had then different research associate and fellow positions at Imperial before joining University of Manchester in 2013, I think. Alex is now reader in the Materials, Devices and Systems Division of the Department of Electrical and Electronic Engineering. So Alex specializes in the design of wearable sensors, bioelectronic interfaces, sensors for human body monitoring, and the analysis of data arising in such context. And today he will talk about accelerometer data from the UK Biobank. So thanks very much, Alex, for being here. Much appreciated. And the screen is yours now.
Right. So thank you very much for the invitation to talk, and thank you all very much for coming along. So I think I'm aiming to talk for about half of the time and leave a good chunk available for kind of questions and discussion. And today I'm going to be focusing on the 100,000 accelerometer data sets that are available in the UK Biobank, and not focusing on the findings that we've got from some of that data, but focusing on some of the kind of computational design, some of the analysis techniques that we've put in place in order to analyze that very large data sets, more than 20 terabytes in a manageable space of time. So I'll start off by just kind of giving a little bit of background about myself, but particularly about the data sets, just to make sure everybody knows what is available, and then move on to what makes it hard. And it's principally there's a lot of it, 100,000 records, 20 plus terabytes is a big data set. Then to overview our computational approach for handling this, some of the kind of tools that we've both used and have made available for other people to use. And then also to finish off, talk about some of the kind of gotchas, some of the kind of things you need to be aware of in order to kind of make a valid analysis. Just to put some kind of acknowledgements, and I thought I'd put all of the resources at the start on a single kind of easy to find page. Firstly, just to note that actually a lot of the hardcore work on this has been done by my postdoc, Chris. Chris is actually on holiday this week. He's cycling around Scotland. So if you have any specific questions for him, please email them and he'll pick them up next week. And I'm sure he'll enjoy coming back to a full inbox. A lot of the stuff that we have put in place are building upon particularly a GitHub page that Oxford from the Biobank Steering Committee have made available. So there's a link to that kind of foundational resource there. And then some of our specific resources, we've got links here. One of them's not quite active yet. It is fully populated, but it's just kind of embargoed until this paper, which should be coming out. Unfortunately, that paper hasn't been unembargoed yet. When you publish stuff with the biobank data, they ask you to give them kind of 2 weeks notice before anything is put into the public domain. And we've not quite hit that, I'm afraid. It would have been good to before this presentation, but we didn't quite make it, I'm afraid. But I would kind of highlight particularly that preprint as a good follow-on resource to this presentation, but it does do a nice job of highlighting a lot of the how do you practically analyze the biobank data, what different factors do you need to take into account. And then lastly, just to my colleagues from Research IT at the University of Manchester, who have been extremely helpful in the setup of all of our biobank stuff, getting it off the ground. And also I have taken 1 or 2 figures from materials that they've produced. And also just an important note for those of you kind of already working with the biobank, actually the way that you work with it is changing. They're trying to move away from you download the data. So we've got this kind of, it's nearly 30 terabytes in total of accelerometer data, plus metadata, lots of stuff associated with it. And it took us like 3 months to download all of that. And actually that's a fairly small part of the biobank. So they're trying to move to a model where you go to the data. So they're setting up, I think it's an Amazon-based system where rather than everybody having to download it, you log on to their cloud platform. And so some of the kind of access questions, some of the how do you optimize the computational platform might be changing in the upcoming months. The kind of software approaches won't, so they should apply in exactly the same way. And then just to introduce myself very briefly. So I'm in electronic engineering, and essentially we're kind of interested in all things wearable. So this is my cross-section of a wearable device that we have on the screen here. Getting data from you, whatever form that might be, heart rate, accelerometry, gait, passing it up to the cloud, where we can do some analysis, and then passing some form of information, which may be a direct treatment, in fact, back down to the person. And I started off in this space kind of 15 years ago, looking very much at the low power electronics. You know, what does the actual instrumentation that goes into these systems, what does that look like? How do we make it fit within the limited power budgets that we have? Today, my lab has activity across the entire spectrum of that cross-section. These are all active projects to differing levels of extent. And so, of course, today we're really focusing on some of the right-hand side stuff, some of the kind of signal processing-based analyses coming from wearable data. Right, so just to overview the accelerometry data set very briefly. So for those of you familiar with the biobank as a whole, so they recruited about 500,000 people in total. Sometime after that, about 5 years after that initial enrollment, 100,000 people took part in an accelerometry experiment. So they were sent a wrist-worn device, this one that we can see on the screen here, that would record 3-axis accelerometer data for a period of a week. And how it works was that this device was put in the post to them, and it was automatically set to start recording 2 days after it should have arrived. So if I put something in the post today, first class, it should be there tomorrow. So it would turn on automatically on 2 days later, that'd be Friday, Saturday. To wear it on their dominant wrist for a week, and then to put it back in the post afterwards. There was no wireless streaming of data. It was designed for them to put on and forget about, for them to kind of wear while they're in the shower 24 hours a day. The battery life didn't need charging. There was a USB port on it, and the device would stop recording if you plugged it into the USB device. And that's it for the accelerometer directly. What there are, in addition to that, are, of course, all of the other biobank fields. So there's lots of self-reported data. So there's a mental health questionnaire data. There's data about enrollment, people's height, weight, and so on. And almost certainly in any analysis, you'll want to be using some of that metadata as well. And then also when you analyze biobank data, you're supposed to return your derived fields to the biobank. And what that means is that today, in addition to the main biobank data, the main accelerometry data, if we go to the biobank webpage, the accelerometry data comes under additional exposures, physical activity measurements. There are some derived metrics that come from the accelerometry data, such as how long people actually wore it for, some averages. And if those are suitable for you, they may well be very desirable to use rather than analysing all of the raw accelerometry data. So that's what's available. And it's just kind of broken down in terms of a number of data for kind of, there were 103,000 people, a little bit more than that, who actually took part. And then depending on your inclusion criteria, and you probably have an inclusion criteria for wear time, just how long did they actually do the experiment for, you might end up with some lower numbers than that. And so a typical analysis flow would be like I just described. So loading the raw accelerometry data. It requires some processing, typically to remove local gravity. So that gravity is an acceleration force, it will be recorded by default, but it doesn't reflect the activity of the person. But then also resampling the data. So any wearable device suffers from clock drift in exactly the same way as your watch does. It won't keep the precise time, it will just vary a little bit, particularly over long-term recordings. But they include enough information to correct for that. And so there's a resampling process just to make sure it is sampling at the 100 hertz it's meant to. And then it's up to whatever analysis it is you would like to do. Putting it through whatever feature extraction, prediction, combining it with whatever additional information, aids, weight for your particular analysis. So if we touch briefly on the kind of computational challenges in the data set, I mean, these aren't anything kind of surprising, as it were. Firstly, it's just that there's a lot of data. So the raw accelerometer data is a bit more than 22 terabytes. And then depending on what you apply for what other meta fields, you could be combining it with the genomic data, for example, in which case you're going to have probably the same amount of data again, probably. We haven't done that. We've only looked at combining it with some of the self-reported questionnaires and similar, but we've still got about 7 terabytes of that metadata coming in. Now then, linked to that is it's stored in a format known as CWA, which is very good because it's very compact. So, you know, that 20 plus terabytes is in an extremely file efficient format, but it is a relatively hard format to work with. Particularly, I think if you're kind of giving some of this stuff as student projects, and you know, we've had master's students look at do bits of this analysis, for example. Depending on how computationally competent they are, some of them struggle with loading a CWA format, and it's a mini work package in itself just to get the data loaded, so certainly at scale. So there's probably 3 different types of analysis that you might be interested in. So firstly is the metadata only. So you can download from the biobank, not the raw accelerometer data, that time series sampled at 100 hertz for 3 different directions, but just the wear time or the average acceleration per hour on different days of the week, or those different categories that we have in the kind of data explorer here. And actually, that's what most studies using the accelerometer data do. I think the last time I checked, and it was about a year ago, there were only 3 or 4 groups who were actually analysing the full data set, loading the raw data, passing that through, rather than just doing a derived measures thing. If the derived measures will kind of answer your research question, that's almost certainly a better thing to do. I'm not going to go into that particularly in this presentation, because I think we want to focus on the harder computational task. But I do have some guides for accessing that data if it would be helpful. So the 2 other types of analysis, firstly, would be kind of a small scale analysis. So this would be something where you don't want to analyze 100,000 people. You want to identify, say, the people who identify as having a particular condition. So we did an analysis looking at people who self-reported, people who have a serious mental illness, such as schizophrenia. And actually, the number of people there is relatively small, because the 100,000 people did the accelerometer recording. About 100,000 people did the mental health questionnaire, but they're not the same 100,000 people. So we could only analyze the subset that's common between those 2 groups, and people who tick the box to say, yes, I have a diagnosis of a serious mental illness. And so actually, for say this top paper, we were only analysing a few hundred people in total. So those people in our test case who ticked the validity criteria, plus some form of a matched control group, essentially randomly selecting people from the other 100,000 records or so that were available, matched them for age, sex, so on, and taking it on trust, or as a limitation of the work, that the randomly selected control group didn't have a serious mental illness that hadn't been reported. And actually, particularly in the top group, we actually have 3 control groups to help kind of mitigate against that. So for this small scale analysis, this is probably desktop PC based. You know, you're probably not getting into your HPC stuff for doing this. In which case, there's a number of tools available. In my experience, where people tend to go to first is there is a GUI app that the makers of the device have made available, and it will export the CWA files to CSV for you. And particularly for students, that tends to be their first port of call. Now, it's extremely inefficient to do that. The conversion takes an age, and storing it in CSV format is probably 10, more than that, times the size of the CWA format. So you really need a lot of disk space if you're gonna go that route. But for 1 or 2 files, CSVs are certainly very easy to work with. Now there is code available that third parties have made for kind of loading the data in MATLAB and in R. Actually, about a month or so ago, the makers of the device have released a Python load module. That wasn't available at the time that we did it. So instead, we were building upon the Oxford toolbox that I mentioned at the start. And so they have a GitHub site that kind of loads data in Python. And actually it builds upon Java for doing the actual load and passing the data to Python. The thing that we've done that might be helpful for this is just port the data load files here to make them work on Windows. The Java calls are platform specific. So if you just download the Oxford code directly, you won't be able to get that running. So we've just done a small Windows port. And again, for people who are maybe getting started in some of this stuff, that might provide an easier route compared to having get it going on Linux first. And what it does mean, of course, is that we're then using the same code fundamentally between our small scale analyses on a local computer and a large scale analysis on some HPC. All we've done is change some of the Unix specific flags to be Windows ones. In terms of kind of computation, of course, the big task is analyzing the full data set. So to do this, we were using the high performance cluster, the computational shared facilities, as it's called at the University of Manchester. And again, we've made available our scripts for doing this. And not just the script for loading the data, but the script for batching it off in what to us is a relatively optimal way. So assuming that your computer cluster is using the same batch submission system, you can use this for automating the entire flow, not just the kind of the loading the data step. Now, getting this to go on the HPC is really a matter of understanding the architecture of your HPC and where the job is limited. So this is very much an IO bound task. We spend our time getting the data to the right place for us to analyze it. We don't have 20 terabytes of cache, as it were, right next to the processor, where we can keep everything at extremely high speed. So you've got to kind of look at the architecture of the HPC and make sure that the data is stored in the high throughput memory connected directly to your compute nodes. And almost certainly, just making sure the data is stored in the correct place is the single biggest step you can do to accelerating the analysis and getting it to go in a manageable runtime. And we get to go through the entire data set in a period of about 1 to 2 weeks. And of course, that will vary depending on how complex your analysis is. Once the data set is loaded, then we're running in Python, so we're single thread bound by and large. And so actually, it tends to, once it's going, it runs slower on the Xeon based HPC than it does on your i7, i9 desktop computer, because they're optimized in different ways. Your i9s are optimized for single thread performance, whereas your Xeons tend to be optimized for kind of multi-thread performance. It's still worth it because, of course, we can send so many jobs in parallel to the HPC. And I think that these days we have an i7 subcluster on the HPC that we can request explicitly. If I remember correctly, that didn't exist at the time we were putting various of these things in place. So our analysis pipeline builds upon the Oxford one, where there's a Java program to fundamentally load the data, and then to calibrate it to local gravity, and to do that resampling process to make sure it is at exactly 100 hertz. It's not varying with battery voltage, with time of day, with temperature, all of those non-ideal factors. What we then do is we save it out as a NumPy file, some HDF5 format thing. And then it comes back into Python and we load in that NumPy file. Now, what would be very nice, of course, would be to keep that NumPy file that's been calibrated, delete the CWA ones. We're not actually interested in them anymore. But actually, even those high density file formats are about 3 times the size in our experience compared to the CWA. So you need a very friendly IT department who's going to let you increase your storage from 20 terabytes to 60 terabytes. And in practice, we don't store them. We have to get rid of them on a run by run basis, essentially. And then we just store our summarized results, whatever it is the result of our analysis. Our analysis runs in this kind of 2 to 3 minutes plus, however long your thing is going for. We analyze at the full 100 hertz data rate, which again is relatively unique. A lot of people downsample before that, so you'll see a lot of people giving an output once per minute, once per 5 minutes, or whatnot. And again, it's just a speed thing. What we do is we downsample for plotting. So we only typically plot the outputs once every 30 seconds, just because otherwise, if you're doing a full time series, we can look at an example plot potentially. You just get too many things to it to actually for it to plot, and it just takes forever. I'm running a tiny bit long, but some of this stuff is basically kind of bread and butter type stuff in terms of optimizing the run, which is to say you need to think about how do you optimally do your parallel processing. So, of course, what we have, and again, this is about knowing your HPC, what is the structure of it, and how do you optimize the job for that. So, we've got about 100,000 or so records we want to get through in total. Each compute node has 32 cores, but of course, there's then multiple nodes. And so, we can choose to run the program on multiple cores of one node, or have multiple copies of the program with them kind of communicating to each other as is necessary. And of course, there are techniques in whatever language it is you're doing for writing your code to meet that. What we're largely interested in is running the same program over multiple compute nodes. We're interested in doing exactly the same thing, just many times. They are all independent of one another until we get to the results saving and combining stage. And so actually the kind of message passing part can be very small, just at the end. And I won't go into too many details about requesting parallel resources, but you can add on switches to the batch submission system. So in our example code, there's an example at the end. You can add additional switches just to pick between, are you going to be using a single node? Are you going to try and do multiple nodes passing jobs between them, and so on? What we make of much more, though, is this, which is just getting the same job to run across multiple nodes. And this is what we kind of built into the batch submission part of our GitHub site, rather than the kind of the data loading, part of it. And essentially, it's about giving each separate run its own ID, which means you can give each one its own individual output file, and you can then combine. So for each individual run, we would have a list of CWA files that we want to analyze in that particular run. So this is the participant ID. This is the data 90,001 is the data field. So that's the raw accelerometry data. That's just what the biobank called it. And then a very simple batch submission script just passes each line of that in file to the load format, and it does it across the kind of 10,000 different runs that we want to put in there. And then thinking about how you optimize that. So our CSF allows jobs to run for a maximum of 7 days. And of course, you also get backed off in the queue. So if you run, what you don't want to do is 100,000 runs of one file. Because by the time you've done 10 of them, you have such a low priority in the queue that it will take you forever to get to the start, to get to the top of it. What you actually want to do is as few as possible, 7-day runs, analyzing as many files as you can in that one individual run. And it's worth doing some optimization, some initial runs, just to see, well, how long does it take you to get through the queue? How many files do you want to be putting into the run script so that it doesn't max out? Yeah, so here we've calculated that on our HPC, we can run about 700 jobs before we get to the 7-day limit, and it automatically terminates it for us. And then we're doing that on a high memory node just to help accelerate it a bit further when you're doing these things in parallel. And that's all I wanted to highlight in terms of the computational part. Let me just very quickly whiz through to some of the challenges that you want to bear in mind when analysing this data, because it's very easy to come up with analyses that sound great, but unfortunately aren't quite what you think they are, aren't quite valid. And it's the curse of having too much data, because there's stuff you don't necessarily know about when you're compared to when you're collecting 5, 10 people, and you know everything about what happened. So firstly, people can still withdraw their data from the biobank. And so you'll see different papers with different numbers of participants, and that's because they've been performed at different points of time. Not that many people wore the accelerometer 24 hours a day, 7 days a week for the week that they were meant to. So depending on what your wear time criteria is, you're probably analysing quite a lot less than 100,000 records. If you want the full 24 hours a day, 7 days a week, you only go about 20,000. We actually analyse about 60,000 by the time we've got rid of people who took it off, that sort of thing. I've mentioned about resampling the data. The one thing you do want to be slightly careful of is all of it. When you resample data, if you're familiar with the maths of that, you have what's called an interpolation filter. And the different tools, whether that be MATLAB, Python, R, will have different default settings for their interpolation filters. So you won't get exactly the same signal if you load it in R versus if you load it in Python. They are the same from an information theory point of view. The data, the information is the same. If you plot them, they'll look extremely similar, but just putting the data at very slightly different points because of how that interpolation point has run. And again, you can trick yourself up there for thinking it's not loaded correctly. The timestamps are stored in Unix time, and that introduces kind of challenges when British summertime starts and ends, because for some readings, they've not got 24 hours in a day, they've got 25. And some of they've got 23. And so your analysis might well need to take care of that. Actually, we just discarded those for simplicity, which is why we get, one of the reasons why we only get 60,000. And we could do better, but it's an awful lot more work to do a correction for that. I mentioned, you probably want to make use of some metadata, but that metadata doesn't necessarily correspond to the same population group. So the overlap between the mental health and the accelerometer data sets is actually relatively small. And that's the one we were using. But also, there's often different ways of coming up with the same metadata. So we've done an analysis for people with diabetes, and we took our inclusion criteria as the enrollment questionnaire that people did when they joined the biobank. Do you have a diagnosis of diabetes? And people say yes or no. That's not the same thing as the primary care records that are also available in the biobank. And if you mine the codes, the different disease codes that are in the primary care records, you will get a different set of people who have diabetes. And of course, if you look closely, there are people who can tell you much more about this than I can. But of course, primary care data isn't that great. So actually, there's not one code for diabetes. There's lots and lots of different ones. And there's nothing you can do about this, but you need to make sure that you're kind of open and aware of the limitations. One of the big ones is that there's a big gap between when people were enrolled and when they actually did the accelerometry recording. The average is about 5.7 years for our group, which means you can't assume people were the same weight. You probably can assume they're the same height. We do get a bit shorter over time. But all of these sort of things, you've got to think about what was the time difference. So it's one of the reasons we switched. We didn't have diabetes in our application originally, but we put it in there because it's rare that people get remission with diabetes. It's not unheard of, but by and large, once you've got a definition of diabetes, you have that for the rest of your life. And that's not necessarily the case for some of the other things that you might be interested in looking at. And again, if you don't take this into account, you can easily do something which you think sounds great, but actually it isn't quite what you want it to be. They don't tell you the birth date of the participants, and so we have an average of 16 days error in estimating the birthday of people, because we only know the month in which they were born. Hopefully this one is getting better in the future. We did get permission from the biobank to kind of store this as a shared resource. So having spent 3 months downloading it and working closely with research IT to get enough space to store it, we didn't want everybody else in the university to have to go through the same process. Nevertheless, there's still quite a process to go through to actually share the resource with people. There's a mapping that's required from the biobank, because in order to avoid leakage between different studies, each different study has different participant IDs. One which we found and we hadn't seen reported previously, this comes about because we're doing it at quite a high temporal resolution, is that it looks like people took the devices off early. So they were told to wear them for 7 days, but actually it went from 10 o'clock on a Wednesday morning to 10 o'clock on a Wednesday morning, which is actually a bit more than 7 days. And from our measures of the data, we can see that we get much less activity on the morning of that last day. And we only get that on days corresponding to a week after it started. So they didn't do any people starting on a Sunday, I don't think. And so you don't see that a week later. There's no discontinuity there. So again, if you're using the full kind of 7+ days of data, you just want to be aware that although it might kind of appear as if it's being worn, actually we see noticeably different patterns on that last day, as most likely they stop using it at some point. Right, and that's all I wanted to go over. I've spoken for somewhat longer than I was aiming for, I'm afraid. But yeah, it is a very large, high-value data set. There is lots of open stuff out there. We try to be as open as we possibly can, and we're building on lots of open tools from other people. And certainly what we have done is we've learned a lot about how do you analyze the data quickly, and what do you need to be aware of to make sure your analysis is as valid as it can be. And I've not put the link on this page, but as I say, I do think that this preprint article, when it becomes available, probably next week, does give a nice run through of all of those different factors, if it'll be helpful.
Good. Yeah, thanks very much, Alex. That was fantastic and really interesting. Let me ask a first question then, Alex. So just in terms of software, so you have obviously used Python and also implemented these Python batch software pieces to load in the data and also to analyze the data. So if someone is coming from R or from MATLAB and would really like to keep using R or MATLAB for those purposes, would you still recommend to do that, or is Python rather the thing to go for?
So from my point of view, we kind of historically we were in Python because historically we were MATLAB users, and right. Essentially, Python we're using Python as the open source equivalent type thing, and then of course we're coming at this more from a machine learning type background, which is all Python, as opposed to a statistics, say, type background, which is all R. I think there's absolutely no reason to. I think R is very well supported. Mm-hmm. There is an I/O module that you can use there. It would seem rare to me that people use MATLAB, actually. Okay. I'm not necessarily sure what the reason for that is. But I think you see this even with the students, actually. I think they do tend to come up with an open source mindset. And so their starting point is, what can I do with Python and similar? So there is a MATLAB. So people have made code for loading CWA files in MATLAB. So far as I'm aware, they're less supported, if that makes sense. I think there's much more of a community behind the Python and the R approaches. Okay, thank you. There is a related question in the chat. So why do you use different languages in your pipeline, Java and Python? So the source answer is because that's what we were building upon. The framework. So we didn't write the full CWA load code ourselves. We're building upon that Oxford tool group, Oxford group. They had that implemented in Java. Now, what their motivation was, I don't necessarily know. If you look, then the difference between the Windows implementation and the Linux implementation that we have is purely about some of the Java switches and taking off some of the HPC switches. So I assume that for the load stuff that they're doing again and again, they wanted very high performance in compiled Java. And I say for Windows, we turn off some of the garbage collection and blah blah blah. That isn't relevant there. I've not used that specific device. I think my initial thought would be one of, it depends a bit on how much validation it is you need of what you do, if that makes sense. So splitting the stuff into sedentary, moderate, high exercise is fairly turn the handle with some of the tools that we have online there, and it's just a matter of kind of learning how to use them, and getting the data into the format, doing the data manipulation so that you can get it passed through correctly. That assumes that you're happy to take those on trust, as it were. And in particular, because you're crossing units. So you would think that one accelerometer is the same as another accelerometer, but I wouldn't necessarily take that for granted, if that makes sense. I would certainly suggest doing some checks that the data, if you take a CWA file as provided by the biobank, say, versus whatever format data yours is providing, just making sure that actually, they do look the same. They have calibrated for gravity in the same way. They have corrected for the sampling rate, and those sort of things, which would just mean that, again, you don't necessarily trust the. Although there's nothing wrong with the analysis and the scripts, that doesn't necessarily mean you want to blindly put any data into it and just automatically trust the results. I think there's a checking the data matches up firstly. And again, you see this a lot with the machine learning type methods, where you just got to check that the model generalizes to different data sources.
So there are some further questions in the chat relating to more general aspects of Biobank. So first question, have you considered some other tools like P-Link, GCTA to handle Biobank data?
No, is the short answer. Anything beyond that, I'm afraid.
That is an answer. Very good. And there's another question on the relating to funding. So is it about the funding model of Biobank?
Yeah. So this work was funded by the EPSRC, both directly. So we had a standard mode grant where we said we would get access to the biobank and analyze it. And then also I had a PhD student who was funded by the EPSRC with a DTP, and we added him to do some of the stuff. So it's 100% legit to, when you're writing your justification of resources, to say I need however many £1,000 it is to access the data. When we were doing this, it was something like there was a £200 application fee, which they've now waived, I believe, and then a £2,000 bulk download, just to costing, paying for all of the bandwidth that we were using. They've now changed that with their new model, because you're also paying for the computational resources. And if I remember correctly, but don't quote me on this, check the email, it's something like £8,000 for 3 years to access the data, but that includes your Amazon Web Presence. So it actually includes the computational resources as well. But that's, reviewers shouldn't be kind of questioning that if you justified your use of the biobank and what is the best resource to use. I'm not aware of any link between the research councils and the biobank directly. I think these are different organizations, essentially.
Right, and so these fees, like these £200, £2,000, £8,000, these are usually expected to be covered by the corresponding university departments or research grants. Is that the expectation?
I think there's an expectation that it gets paid.
Yeah.
where you do that from, kind of locally or not. I say we've been fortunate. We've always been able to have external funding for it. I guess it depends on your local arrangements. You know,